Alright, so we're continuing with our review videos for Math 1560, Calculus 1 for the fall semester at the University of Lethbridge. In this video we're going to introduce polynomials, and for the most part we're going to focus on the two simplest cases of polynomials, which are the linear and the quadratic polynomials, and we'll maybe look a little bit at the general case. So in general, a polynomial is any function that can be written in the form you see here, okay? So it's a combination of powers of x, integer power, positive integer powers, okay? So n here is a positive integer, so you can have a constant term. There could be an x squared, maybe x cubed, up to some maximum number, which is called the degree of the polynomial. That's this number n here, that's the degree. These numbers a0, a1 up to an, these are real numbers. They're constants. These are the coefficients of your polynomial. Okay, so every polynomial is basically constructed by first writing down some powers of x. Then you multiply each of those powers of x by some constant, and then you add all those guys together. This gives you a polynomial, okay? So examples of polynomial functions would be things like 3x squared plus 2x plus 1, or g of x equals x to the fourth plus, say, root 2x squared. Don't let that root 2 throw you off. Square root of 2 is a perfectly good real number. You can use that as a coefficient. Lots of our examples are going to involve integer coefficients because we like to keep the numbers simple. They don't have to be simple, right? Any real number can show up. The important thing is that the powers of x, those have to be positive integers, okay? So if I give you something like, x to the 1/2, or g of x is, like x plus 1 over x, right? Where I have fractional powers, of course, x to the 1/2 is better known as the square root function. X plus 1 over x, right? You see negative powers in there. These are not polynomials anymore, okay? And then, of course, anything involving like exponentials, logs, trig functions, these are definitely not polynomials. Okay, now, one of the things that's nice about polynomials, we'll see moving forward, is that polynomials are very well-behaved functions, okay? They're continuous. They always have derivatives. Their domain is everything, right? There's never a point where a polynomial is not defined. They're nice. Their graphs are smooth and bendy, and they're easy to work with. Algebraically, polynomials can be a bit tricky because one of the things you often have to do with a polynomial is factor it. And, well, we'll talk a little bit about factoring quadratics, and I'm going to guess that most of you don't have too much experience factoring beyond degree 2. And to be honest, in higher degrees, it's a bit of a crapshoot. Sometimes you can get it to work, but in general, if you want to factor big polynomials, the only real practical way to do it is using a computer. Okay? Now, the simplest polynomial, well, okay, the simplest polynomial is the constant function, right? So a constant function is technically a polynomial. Something like p of x equals, just a constant, like 2. And those could be considered a special case of linear functions, simply set a equal to 0. Right? But constant functions are kind of boring. So beyond the constants, the next simplest polynomials are the linear functions. The reason they're called linear, as I'm sure you all know, is that when you graph an animal like this, you get a line. This number b, if I set x equal to 0, if x is 0, I'm on the y-axis. The y value, of course, is given by b, right? So b is the y-intercept. So somewhere there's your point 0, b. The number a is the slope. You might often see it written as m, right? So you get something that looks like this, right? And so where the slope comes in here, if I choose 2 points on my line, so if this is a point, say x1, y1, and this is a point x2, y2. The slope is rise over run, right? So it's given by y2 minus y1 over x2 minus x1. And what sets linear functions apart from all other functions is that this ratio is going to be the same no matter which 2 points you choose. Right? So this ratio, this rise over run, change in y over change in x, it's always going to be the same. And if you want to see that it's going to be the same, we can plug it in. y2 is going to be, because these are related by this function here, we know that y2 must be ax2 plus b, and then minus ax1 plus b. This is going to be a good little algebra exercise for you guys. Okay, push that minus sign through the brackets. ax2 minus ax1 plus b minus b. Be careful, right? That minus sign hits both of these guys, and then those b's cancel out. x2 minus x1. And now what's left on the top is that guy there, a times x2 minus x1. Right, if I factor out the a, x2 minus x1, x2 minus x1. And now that I factor out the a, look, x2 minus x1, it's the same thing top and bottom, right? Always comes out to give me this number a, right? So slope is constant for linear functions. One of the reasons we like linear functions, they are super simple. Okay, now let's jump ahead. Quadratic functions. We go up 1 degree. So before the highest power of x we saw was x to the 1, we add in one more, x squared. Right? So quadratic functions are, graphically, these are our parabolas. So we'll talk about that in a second. Right? So the graphs look something like this. And there's a few different ways that you see quadratic functions presented to you. One of the ways that you often see a quadratic function presented is in this so-called vertex form here. The reason why this is nice is you can see that if you plug in x equals p, f of p equals q, gives you 1 point on your graph, the point PQ, okay, and of course, right, because p minus p is 0, 0 squared is 0, but for any other value of x, of course, this is some number. It might be positive, it might be negative, but it's being squared, so it's always going to be positive, and let's assume that a is also a positive number. So we're going to go up from there, right? So this point PQ, that's the so-called vertex of the parabola, right? It kind of tells you where that parabola bottoms out. And of course, you can get from the vertex form back to this so-called standard form. You just have to do a little bit of algebra first, right? If we do that square, and remember, squaring a binomial, because I know somebody is going to make this mistake. Even if I point it out, you're still going to make the mistake. Squaring that binomial means you're multiplying the binomial by itself. That means you multiply that thing out using FOIL. You don't simply square the first term and the last term, or you miss the cross term, the x times p that shows up twice. There's a minus 2xp in there, plus p squared, plus q. Right. So, ax squared. So I get an ax squared. I get a minus 2apx, there's my x term, and then there's also ap squared plus q, right? I get this constant term. So going from vertex form to the standard form, that's straightforward. What about going the other way? Do you guys remember how to do that? That's completing the square. So somebody hands me a function like this. Can I get from the standard form to the vertex form? Do you guys remember how to do this? So 2x squared minus 8x plus 3. Well, the first thing you do is you factor out, if there's anything in front of the x, bring it out. X squared minus 4x. Don't worry about the 3 though, just take it out from the x terms. Plus 3. Okay. Now, I want to be able to take this and write it as something squared. right? So I want to say, so x squared minus 4x plus, well, something to be determined. I want to write that as x minus something all squared. And if you kind of play around with squares and you think about what happens, well, this cross term, this 4, is always twice whatever number shows up here. So what number do I have to double to get a 4? I have to double a 2. So here's what we do. I'm going to put a 4 in here. Okay? Because I know that that's going to make a 4 for me. Okay, so if I put a 2 in here and I multiply this all out, I get x squared minus 4x plus 4. So I'm going to put a 4 in. Now, I can't just throw a 4 in. If I put a 4 in, I've changed the function, right? I've added 4. Really, what I've added is 8 because there's a 2 out front. Well, I can't. If I add 8, I've changed things. So how do I fix that? I subtract 8 as well, right? Then this 8 cancels with that 8. I haven't made any changes. One last step, okay? X minus 2 all squared. I know I worked that out ahead of time. And minus 5. Now I'd be in a position to graph this if I wanted to graph it. I could graph it using transformations. The other reason why you might want to complete this square is completing the square is actually how you come up with the quadratic formula. Okay, I'm going to skip the details, but using completing the square, you can actually work out that for a general polynomial, if you're looking for the roots, there's a couple of ways of finding them. Here's the quadratic formula, right? So the value, so t here is one of the values that makes this polynomial come out to be 0. So 8, so I'm solving here a t squared plus bt plus c equals 0, right? I want t to be a solution. Well, then the quadratic formula does the job. Notice that I'm not guaranteed zeros here because, well, I might have a polynomial that doesn't intersect the x-axis, right? If I have zeros, that means my polynomial, my quadratic looks like that. I get a couple of roots, right? But my graph might be up here. It may not even touch the x-axis. I don't actually get zeros. How do I know if I'm not going to get zeros? Well, I calculate this value, b squared minus 4ac. If that thing comes out to be negative, I say, well, I can't take the square root of a negative number, so there are no answers. Right? Quadratic formula will give that to you. If you're lucky, you could also try factoring, right? And factoring is a bit of an art form, but with some practice, you can get the hang of it. So what you want to do is you want to say, well, can I write this as, a product like this, x minus a times x minus b? Can I come up with that? Right, and the reason why you would do that is that if you then set this thing equal to 0, why does factoring help you? Well, if this whole thing is equal to 0, you got a product of two numbers equals 0. The only way that two things can multiply to give you 0 is if one of those two numbers equals 0. So either x minus a would be 0, in which case x equals a, or x minus b equals 0, in which case x would have to equal b. And if you think about multiplying this thing out, what do you get? You get x squared. Your cross term looks like this, a plus b times x, and then you do a times b, right, ab. So you kind of compare the general picture to what you have, and you say, all right, I'm looking for two numbers, a and b, so that when I multiply them, I get 6. When I add them, I get 5. And you say, I know exactly two such numbers, 2 and 3. So this is going to be x minus 2 times x minus 3. Right, and so then if I was trying to find the zeros, I'd say, well, one of these two has to be 0, so either x is 2 or x is 3. If I try to do that with the quadratic formula, that works too. Quadratic formula would say that x should be, that's a terrible x. X should be what? B is, in this case, B is minus 5, right? B is minus 5, C is 6, A is 1. So minus 5 gives me 5 plus or minus the square root of, so minus 5 squared, 25, minus 4 times 1 times 6 over 2 times 1. So 5 plus or minus. 4 times 6 is 24. 25 minus 24 is 1. 5 square root of 1, also 1. 5 plus or minus 1 over 2. So either 6 over 2 or 4 over 2. 6 over 2 gives me the 3. 4 over 2 gives me the 2. So if you can't see how to factor, you can always fall back on the quadratic formula.